So I'm going to talk about the joint work with a gun, and is based on the previous work joint with David Kazhdan. This will be mentioned later. Now, while this workshop is somehow dedicated to Eisenstein series, the majority of the talk will be local work, but at the end we shall see connection to Eisenstein series too. And I know it is last lecture in the day, so you must be tired. I'll try to keep it elementary as long as possible. So I will start with the Fourier transform part. There is no need to advertise the classical Fourier transform, but I will emphasize its properties that are relevant from the representation theoretical point of view. So during most of my talk, F will be a periodic field or any local non-Archimedean field, and I fix an additive character of the field F. Okay, so let me start with a review of a classical Fourier transform. Let V be a finite dimensional vector space over F, dimension n. Okay, and V admits a natural action of the group GLV. I will be writing the action on the right times the multiplicative group, where the action of the multiplicative group is just scaling. Okay, and such an action induces a unitary representation on the space. So let's fix a higher measure. At the moment, I don't care about the normalization of it on the on V. Consider the space of square integrable complex valued square integrable functions on V, and we have a unitary representation of the same group defined naturally. Just GT F of V would be F of Vg times T. T is a scalar, and we need to normalize it, so to make sure that the action is unitary T in n over 2 and the determinant of G in half. Okay, so now the same game can be played for the dual group, right? So for the dual space. Okay, on let this be a dual space, so we have a canonical pairing, and there is an action of also GLV, or if you want to denote it by GL V star, and again we have an action, unitary action on the L2 of the dual space, so that the action here preserves the natural pairing. So from the point of view of representation theory, these are unitary representations, and can be you can ask how to decompose that. So this representation is a unitary representation, is a direct integral of is there a question? Is a direct integral and of representation which are degenerate principal series of GLV, okay, induced from the maximal parabolic, which is a parabolic P is a parabolic Pn minus 1, 1, whose levy is GLn minus 1 times GL1, and we integrate over all characters of P, well, complex valued characters, dk. Okay, and similarly, so this is true because G acts transitively on the all non-zero vectors on V, and the stabilizer would be the derived group of this parabolic. So by general yoga, this representation is the direct integral of those representation. And similarly, L2 V star would be the integral over the same set, because the, okay, hold on. The representations are degenerate representations on G, but this time the stabilizer would be the opposite parabolic or derived group of the opposite parabolic subgroup. So, but chi here are the characters of the opposite parabolic group, but they're basically characters of the Levy, and these two parabolics share the Levy, so this is the same set. Okay? Now note that there is a natural intertwining map between components of that representation and this representation. Induction from chi, from parabolic P, there is a natural intertwining map, which is for generic chi is isomorphism, and induction from G P bar. You can write such an element by just average a map by just averaging of the opposite unipotent, okay, with the same chi. So on the level of components, you have here intertwining operator. Of course, this intertwining operator not defined uniquely. This is a one-dimensional space. So you might ask how to normalize them. Well, let me write here just GLV, because whenever you know this as a representation of GLV, this scaling is defined uniquely. Okay, so now this representation, as I said, is not defined uniquely. It belongs into one-dimensional space. So there are several reasonable ways to normalize it, but one of the ways to normalize it is to try to construct a, so to say, global operator from here to here, so that will be itself, that will be equivariant under the action of GLV, so we'll reduce to the operator on this, on the level of each component, and will give me, if I start with a specific operator from here to here, this will give me an operator which is equivariant. This will give an operator of here to here, and this will be properly normalized intertwining operator. Okay, so of course in this case we know which and a priori. So and what do we want from this operator besides asking it to be equivariant? It makes sense to ask that it is unitary, and also involution. Okay, so we know what operator to take. So this is classically, there is a Fourier transform, classical Fourier transform, and we have a classical Fourier transform going backwards, phi and phi star. So let me just recall that whenever I can define this operator by an integral on a dense subspace whenever it converges, but say I want to define it on the space of functions of smooth functions of compact support, so which is dense here. So this is integral over v f of v psi of v star v. We have a natural pairing here, and we define a measure. So now at this point it matters which measure I take. Okay, let me just write the opposite guy. This will be integration over v star f of v star psi of v star v dv star, and the claim that we can find measure which are dual to each other in the following sense, so that the properties will be as I said before. So let me write down the properties. One, phi is unitary, and the composition of the taking phi and then phi star gives us identity. Sorry, I want to use here the psi bar or psi inverse to make this hold. Second, the operator is equivariant under the action of these groups, so I can put it like this. Phi is G star T star. This G star T star is the action on the space L2V star times P. Okay. Yeah, and in fact, this phi can be written as an integral of those operators, whatever it means. I will not go into details, but basically it is glued from the operators on each component, and those operators f chi could be thought as normalized intertwining operators. Okay, and globally, phi of f is the intertwining operator. When I say globally, I mean on the level of L2 of V. It's kind of intertwining operator between these two representations. Okay, so let me stress one more point about this phi, is that it is in fact composition of two operations. So Fourier transforms is something which is very, very familiar to every undergraduate student. It is connected to a bit less familiar transform called Radon transform. But on this level, it's also very elementary. Let's rewrite this integral as follows. Actually, every V star defines a fibration on V by hyperplanes. So we think of V as a union of hyperplanes such that V star on elements of V gives a certain value A. Okay, so we can integrate it in stages. Basically, first integrate over each fiber. Okay, but then fiber itself runs over F, or sometimes we write here F star. Doesn't matter as long as we concerned with the integration. So here there is a measure on each fiber, okay, which let me define, call it mu A of V, okay, and then I further integrate over, okay, hold on, psi of A B. Okay, as you see, this is just tautology, rewriting this operator like that. Yes? Yeah, I mean, I always, let me think of elements here belonging to, yeah, you're right, V star is not zero, but as long as I'm concerned with integration, I can always ignore a set of measure zero. Yeah. Okay, so now please look. So rewriting this as such, there is just nothing here. I first integrated over all elements such that V star V is fixed value A. Okay, and then finally integrated over psi of A. All right, but this part is called the Radon transform of the functions f, while further integration, okay, it is nothing but convolution with a certain distribution, this time defined by psi of A. If we can, let me rewrite this. So all this can be rewritten as something like this. The integration over v star with v by a simple change of variables a of f of v, mu1 of v, times a character which is due to, and here a belongs to gm. And here, because of change of variables, there is further further term power of a. Okay, so this part it is called the Radon transform of, well, this time functions a of v, and you see that we are convolving it with certain distribution. Okay, so I can write it as sort of integral e of a dA. Okay, where e here is this element. So eventually we have rewritten, for no good reason maybe at the point, but the story will repeat itself later. We have rewritten the Fourier transform as a composition of two operations. First operation is taking this Radon transform, which is itself a GLV equivariant operation, and then taking a convolution with certain distribution. On the level of representation, this can be thought of first part taking the unnormalized intertwining operator. So this Radon transform is equivariant, but not GLV equivariant, but not unitary. To make it unitary, we further convolve it with a certain distribution on F. Okay, so note that if we just require those properties 1, 2, 3, okay, this still doesn't imply that the operator must be the classical Fourier transform. Okay, because at to make everything unitary at every point, you can try to multiply the operator phi chi by some constants on the of norm 1. This will not disrupt unitarity, but still the Fourier transform is a very classical and nice operator which does the job, and we'll try further to mimic it to continue this game in other cases. Okay, so just a small remark that you see that the Fourier transform is a map from one space to another space. But if V happens to be a quadratic space, then this the non-degenerate quadratic form defines canonically isomorphism between V and V star, in which case we can think, I mean, under this identification, we can think phi as to be a representation from L to V2 itself. Okay, it is still equivariant, but this is not true that it commutes with the action of GLV. Okay, because the G star is under this identification is not equal to G, but say it commutes with action of orthogonal group. Okay, so phi, there is still equivariance properties, but say phi commutes with O of phi. Okay, in any case, it's possible to look at it as automorphism of some space. Now, if we look at L2V, what we see? We see that there is a natural action of the group GLV times GM, very visible, clear from representation. At theoretic point of view, we see that this space is highly reducible as this representation, and we see that there is further hidden symmetry, which is phi when we look at it this way. Well, they don't commute, but they interchange in a clear way. So the question is, are there further symmetries to this space, okay, which extends the action of these two things and make it an irreducible representation? So this is a very rare situation, but in this case, it actually works. Okay, so there are more symmetries. So in fact, there exists a bigger group, and we can, this is a symplectic group of V plus V star, or we also can think of it as the symplectic group of the symplectic space, which is a product of the quadratic space with two-dimensional symplectic space. Anyhow, this is of dimension 2n, okay, which itself acts on L2V. So to be honest, it doesn't, and one has to add a cover. But let me not enter into this point too much, because in the further examples, there will be no covers. Okay, it acts on L2V, where essentially the GLV part, which is a Levy subgroup, and GM, which is embedded as a center of this Levy, acts as before, and certain elements. Okay, maybe I'll write. So there exists a representation. So this is a famous work by Bell, unitary representation, reducible unitary representation, where GLV acts as before. Further, this group, let me call it H. This H contains a maximal parabolic subgroup, okay, which has with Levy decomposition M and N, where M is basically isomorphic to GLV up to covering, and N is this is so-called Ziegel parabolic subgroup, and the N is abelian. Okay, and the action of N, action of M was given as before. Action of N as is given by we just multiply our function for any element of V by a character of NV with V. Our N can be thought of as a map from V to V star. Okay. This formula, it's just important for you to know that this is a simple formula. The formula itself is not important for the minute. The action of M, as I said, as before, and the action of the element S, which is basically, let me call it S, okay, which is a representative of the longest Weyl element. Okay, the action of Fs acts by. Okay, so what's important about this? This is a very famous representation, and its important properties. This is so-called minimal representation. Okay, so we get pi h L2 of V, as I said, unitary irreducible, minimal representation. There are many of H. there are many equivalent definitions of what minimal representation means, but informally we realize it, or this is so-called the representation of minimal functional dimension, meaning we realize it on a space of L2 functions on a variety where the dimension of this variety is as small as possible, okay? And it happens, this dimension V also happens to be half of the dimension of the minimal orbit in H. Okay? So this is the definition that I told is actually not very precise and it's very hard to work with it, but informally, if you want to think what minimality means, then maybe this is something which is easy to understand. Okay, so now the question is whether this game can be played for other groups. Okay, meaning other significant operators, okay, which has nice acting on some L2 space of certain varieties, having good equivariant properties, which are basically analogs of Fourier transform. And this example shows that minimal representation might be relevant to the game. So let me show how it works. Now, the minimal representation do not exist for all the groups. So I will, and sometimes when they exist, they might exist, like in this case, on covering groups. So I will restrict myself to the case where they exist, unique, and actually defined on the group itself. This is what happens for simply laced groups. And let me take groups H to be adjoint groups of type adjoint split of type Dn, E6, or E7. Okay, in fact, E8 also has minimal representation, but you will see why it is excluded from the list. So those minimal representations, again, can be defined and constructed in many ways, but one of the convenient way to construct them using their models. Okay, and in this case, omega is, again, variety of the smallest possible dimension for the group, and again, its dimension equals to half of the dimension of minimal orbit. So let me explain how this works. By the way, this is not a unique model that can be considered for this space, but it has a name. It is called Schrödinger model. However, I feel that maybe it might be more reasonable to call it a Kirillov model, because the existence of it actually it exists for the same reason that as Kirillov model exists for the excuse me? I'm in Schrödinger. This is a good reason to call it a Schrödinger. Very good. So for the time being, let's call it Schrödinger model. Now, what is this model? So let me elaborate a little bit. Now, the group H contains, as before, a maximal parabolic subgroup where n is a billion. And m, what about m? Okay, let me just note here that at some point I will want to consider the group, say, H tilde, which are automorphism of H, which is a semi-direct product of H with finite group, which are automorphism of Dynkin diagram. Okay, in this case, of course, H tilde is just H, but in these two cases, it's slightly bigger. Okay, so we have a maximal parabolic defined for these two groups uniquely. For these two groups, there are two choices. We fix one of them. And there is a opposite parabolic. Of course, n bar is a billion too. They share a Levy subgroup. Okay? And let me define the G to be a derived group of this Levy subgroup. So who is omega? How do I construct omega? On the level of Lie algebras, this gives me a decomposition of the Lie algebra as Levy part plus n part and the opposite of n, and m acts on n and acts on by conjugation on the algebra. So let me define omega in n bar to be a minimal m orbit, minimal non-zero m orbit. Okay, so here inside n we have omega bar. I'm sorry that this is switched, but again there is a good reason for that. Okay, and the killing form between n bar and n defines a pairing between omega and omega bar. All right. So that's the definition of omega. Now this omega, it is, as I said, this is an m orbit, but in fact it's also a g orbit, and omega can be identified with g acts transitively on omega, and the group G itself. So as I said, it acts on omega in the stabilizer is a derived group of certain maximal parabolic subgroup. Okay, and omega bar in the same way is can be identified with the quotient of G by the stabilizer, which is the derived group of the opposite parabolic. Okay, now we are in the situation which was described by Braverman and Kazhdan. So such spaces in general, G mod derived group of parabolic, not necessarily maximal, are called basic affine spaces. So at the moment I have defined omega, and this was inspired by the fact that minimal representation has a model on this space. But let me forget about this at the moment and move to, I have defined omega and omega bar, and move to work by Braverman and Kazhdan, who defined generalized Fourier transform on such spaces. Okay, so this is Braverman and Kazhdan in late 80s, I think, as a part of their much bigger ambitious problem, have defined FPP bar, a map from L2 omega to L2 omega bar. Okay, yes? No. H is a bigger group. Okay, it's like SP in this case. Okay, M is like GLV. Okay, just a second. G is the derived group of this Levy. Okay, and G acts on omega. Okay, and P is the derived group of P is a stabilizer of a point. So P is a maximal parabolic in G, while G itself is almost Levy in H. Okay, in M in H. That's how it works. In N in H, in Q in H. Okay. Anyhow, this operator is. Let me write this its properties, and then say a couple of words of the constructions. Okay. So this operator is unitary. And in fact, there is a operator which goes in the other direction. Okay, and the composition of them is identity. Okay. Second, this operator is, as I said, this space admits an action of G. Okay, even of M. And, well, let me write it this way. This space is G times, let me write P to be like M1 U1, its Levy decomposition M1 equivariant. Okay, obviously G acts here on the right, the Levy part acts here on the left, and since the derived group of M1 acts trivially, you can somehow think that what acts here is G times a torus abelianization of M1. Okay? And now, again, this group is, this space is in fact integral as a representation of G, say, at the moment. Okay, the story repeats itself as with Fourier transform, and L2 omega bar is integral over the other principal series, and again there is a intertwining operator, so that's why this FPP bar is called generalized Fourier transform, and also is called normalized intertwining operator. Okay. And as for construction, so as Kazhdan told me, when they have been constructing, defining those operators, okay, they've been guided by the example of usual Fourier transform, in the sense that in the construction they also used the construction in two steps. First, taking the Radon transform. Okay, as I said, we have a natural pairing between these two omega and omega bar. So this Fourier transform by Braverman and Kazhdan has been constructed as you first define Radon transform on the of f on, say, some functions x. Okay, so again, this is an integration over f, where f is identified with this torus, which is a one-dimensional thing, and then integration x y equals sum a. Okay, f of y with a measure which measure on the fiber. Note that the fiber is no longer a hyperplane. It is some variety of codimension 1. Okay, so one has to work out what you get, and here you have certain distribution. Okay, and this distribution is no longer just a character or character times a power of a, but in fact convolution of several distributions of this form. Okay, I will not enter into details how exactly to construct it, but the construction uses the structure of the dual group. Okay, in fact, quite predictable by Shahidi's normalized factor, the method of the Langlands-Shahidi method. Okay, so this operator has been defined. Okay, and it is also the composition of Radon transform, which is not normalized intertwining operators, and further normalization process, convolution with some one-dimensional distribution. Okay, so far so good for the Braverman-Kazhdan. Now we are going back to minimal representation. So now the question is whether there exists an element. So now L2 of omega has, again, obvious symmetries of G, of M, of G times this abelianization of the torus. It has hidden symmetries, like this FPP bar. Whether it can be extended to an irreducible representation of a bigger group? The answer is yes, and this representation is again minimal representation. Okay, so basically, let me go back to the group H. Note that in Braverman and Kazhdan's story, the group H as sort of doesn't exist, right? We start with G, which is a derived group of M, and only play with this. But there is a bigger group. So this H has Q, as I have written already, and Q bar. And there is an element S. We specify in each of the cases an element S, which is an involution in the group and conjugates Q to Q bar. Sometimes this element doesn't belong to H, but only to H tilde, to the extended group, because, for example, in E6 case, the group Q and its opposite are not conjugate. But nevertheless, so we specify there exists S in H tilde such that S squared equals 1 and S Q S inverse equals Q bar. Okay, and now there is a theorem almost finalized, so in the which is it is in case for the H of type Dn. This is the result of myself in Kazhdan in 22, and for E67, this is with a gun in the process of finalizing. But the idea is the following: that note though that maybe I should say that while the element, the operator PP bar acts, takes us from the representation omega to omega bar, we have at the moment that we fix such S, we define a natural map from functions on omega bar back to omega, which is just conjugation. This is, let me call it iota S, conjugation by S. Okay. We know that since omega sits inside n bar while omega bar sits inside n, S conjugates one to another. Right? So here S n bar S inverse is n. And so the same is about omega. Okay, so the claim is that the IS, the composition of these two operators is basically I of S. Okay, so in other words, there exists this generalized Fourier transform is just one of the elements acting in the minimal representation in Schrödinger model. Note that in general, when we look at the Schrödinger model, when we define it, okay, only the action of Q is specified. Okay, when we define. When we look at the action of H on this model, we know that the element M in the Levy M acting on X just acts sort of geometrically. Here we need some character to make the action unitary. The element N of F of X acts so-called spectrally. Basically, we define we multiply the F by the pairing between N and X. Remember that N is an element in the abelian radical of parabolic U, which can be identified with an element of Lie algebra. As everything is abelian, there is a natural pairing between the element in omega, which is an n bar, and an element in n. Okay, and S acts by the theorem, right? So this, since this defines an action of maximal parabolic subgroup, so we in general need just one extra element to determine the action completely. Okay, so this determines the action. Yeah, I mean, yes, whenever the n is not abelian, it's everything becomes a bit more complicated. So if you want to know how exactly looks this pi of S, it is a uniform expression. I can write it in general. So this is like, let me call this operator phi. Okay, as a Fourier transform, because, or rather, its restriction to the functions of compact support is given by the following formula. So we integrate, first we integrate over all xy equals a, f of x on the fiber of this fibration, sorry, f of y, and then we integrate it over this distribution, okay, at of a dA as before, and this at of a, let me write it as a distribution, the integral itself as a function, it is not defined, but it is sort of a Bessel function. Okay, so we integrate, this is a convolution of two distributions of the form psi times certain power of x, but when we convolve the two, that's what we get. This is known as a p-adic variant of Bessel functions, and just for the structure of this distribution is the same in all those three cases. The only case, the only thing which differs is this power k. Okay, so let me say several things about a little bit about the proof of this theorem, and then to see possible applications. Excuse me? No, the fact is, actually, the theorem that is not new is that there exists a unitary representation in which realized in this model, such that the element in Q act in this way, okay, and this representation can be, in principle, extended to a representation of G without specifying any element, and this representation is unitary, is minimal. Okay, the thing that we add to the story is that additional element S acts by operator, which is actually has been around for a while. Okay, and in a minute I will show what actually follows from this. Okay, so maybe I'll spend just several minutes about the proof, and then several minutes about the possible application of this story. So let me just write for you kind of table just so that you see which groups are involved and how these n and omega look like. So here is table. We have H, we have G, we have this N, we have this omega, and I will indicate what are dimension of both, and we have this number K, which enters into this normalization distribution. Please. No, I mean, sometimes, for example, in GLV, the parabolic, if you take the parabolic PNM, where n is not equal to m, you need to, the opposite parabolic and the parabolic itself are not conjugate. So sort of the parabolic PNM is conjugated by the longest element to the parabolic P bar Mn. No problem. So say H could be Dn, E6, and E7. Okay, in which case here G is a Levy subgroup or derived group of a Levy subgroup Dn minus 1. You see that the Levy is the unipotent is abelian. Here it's D5, and here is E6. Okay. In this case, the N can be identified with sum of two, where it has a structure of quadratic space. It has dimension 2n minus 2. Okay, Dn has rank n, of course. And the omega are just isotropic, non-zero isotropic vectors. So you have a pairing here, and omega is just all the elements here such that if you wish, V star V equals 0. Okay, this and V is not 0 itself, right? It's a fine closure, can be taken to be the whole isotropic cone, and it has, this one has dimension 2n minus 2, while this has dimension 2n minus 3. In this case, K is n minus 3. So just for curiosity, there is in E6, n is in fact has a bit similar structure. It is has dimension 16, and it is a sum of two octonian, can be given a structure of sum of two octonian algebra, each of dimension 8. Okay, and omega is a subspace of much. Here it was of codimension 1. Here it will be of something of dimension 11, and is given by all the pairs with conditions that their norm of each is 1 and their product is 0. Okay, so but some very specific condition using the fact that each of those spaces has a structure of octonions. In this case, K is 2, and finally, in this case of E6, the unipotent radical has a very interesting structure of so-called Jordan algebra, unique exceptional Jordan algebra, which consists of 3 by 3 Hermitian matrices over octonions. It has dimension 27. Okay, and omega on it, well, like in usual Hermitian matrices, with the action of GL, the smallest orbit is matrices over rank 1. Okay, the orbits are parameterized by rank. So here is 2 is rank 1 matrices, rank 1 elements in this algebra, exceptional algebra, which has dimension 17. So you can see that in each and every case, this omega looks quite different, and we have to, so the proof is a bit different for different groups. In this case, K is 3. But what is common is that, for example, for proof, I will only address the proof for Dn and E7 case, okay? It relies on the comparison of two different models, okay? Compare Yeah, of course, I will not do any computation, but let me just say that a part of this Schrödinger model, there is such that we have an explicit action of the elements in the parabolic subgroup Q. We also have another model, which are functions on a different variety, omega prime, where here you have an explicit action of the Heisenberg parabolic. So P equals LV is a Heisenberg parabolic. Note, by the way, I didn't mention that I have excluded E8 from the discussion because it doesn't have a parabolic, maximal parabolic, whose unipotent is abelian. But it has, as any group has, besides a maximal parabolic, whose unipotent is Heisenberg, okay? And this model exists always, but this model not always. It exists in those cases. Now, there is a particularly simple, again, I don't have time to talk a lot about that, but there is particularly simple intertwining operator between the two, just given purely in by kind of isomorphism, or birational isomorphism between omega and omega prime. Okay, so if we know that Q and P together generate H, okay, which means that if you know explicit action of Q on this model and explicit action of P on this model, and you know to write down intertwined operators, then in general it is possible to use this information to extract the action of any element, in particular S. Okay, but the computation is rather lengthy, it uses a lot of those structures. Nevertheless, this can be done just in principle, from this information. Okay, so can extract action of S. Note that this wouldn't work for E6 because Q and P both generate the group H, but the element S doesn't belong to H. It belongs to the H tilde because it's not. There is no inner automorphism which conjugates. So you have to do something else. Again, I don't have time to do that, but for E6, we first find action of element in the automorphism of the automorphism of the Dynkin diagram. Okay, so so far so good. I have still 5 minutes, and let me say what we get from here conceptually. So for this, I want to go back to Braverman-Kazhdan program, and the reason why they considered these operators, that as a part of their program, they wanted to construct correct space of Schwarz functions on varieties omega. Okay, whatever it means. This is some G space which is closed under G, contains the function of compact support, but contains more things. They wanted to define. They defined it as sum of images. Well, in this particular case, this will be together the space generated by functions on compact support, smooth functions on compact support on omega, and the image of this Fourier transform. So unlike in the case of usual Fourier transform, which preserves the space of function of compact support on V, here the Fourier transform doesn't preserve the function of compact support, it enlarges the space. Okay, but this definition of this space is just sum of the space of compact support and the image of some weird operator, maybe a little bit unnatural, while in this particular case, we have a very natural definition. The corollary, in the case of, in the case discussed, which is only very small part of the much more general construction by Braverman and Kazhdan, okay? But corollary is that the correct, so let this be the function of compact support plus image of plus the operator phi applied to this. Okay, this space which was defined to be a correct Schwarz space on omega. The corollary is that this is in fact just a space of smooth vectors in L2 omega as a representation of this bigger group. Okay, so whenever we have a unitary representation, you have a irreducible. You have a corresponding irreducible smooth representation, but just taking smooth vectors with respect to the section of this group. Okay, so this is a space of H smooth vectors of L2 in L2 omega. So this space is not just that's how it's defined, but it has a meaning as smooth vectors of an irreducible representation of a bigger group. Another thing is that what they were eager to define in general is so-called special basic function in this space. Okay, so in general it is very tricky to construct it, but in this case it is clear what it has to be. The spherical function in, I mean, when we have the representation pi is unramified, is irreducible unramified, so it has unique one-dimensional space of k-invariant vectors and generated by a spherical function f0 in S omega. This is just a spherical function of pi, whose formula for which has been obtained by Savin and Woodbury, and this is the basic function. Function thought in the Kazhdan problem. So, excuse me? I guess it should. I haven't checked this part. So, in general, in the Braverman-Kazhdan work, they write down whenever you have for a variety, you have this S of omega and phi0, you might have a kind of Gottman-Jacquet construction. But maybe this is not for this variety, but the variety which is just a group. So in general, such a basic function should exist. This has been pointed. Something like this. So I cannot say exactly how this is related, but as a part of much larger program, okay, there should be both S of omega and also this phi0, and they have to be related to construction of those L functions. Yes, yeah. So this defines it like conceptually. Maybe really I will take another 2 minutes without writing anything. So let me just say a couple of words about Eisenstein series, how Eisenstein series is related to the whole business. All this work so far has been local, but those minimal representation, or rather representation which are tensor product of local minimal representations and at every place. These are abelic representation, they are automorphic. And they are realized automorphically, they have been realized automorphically by the work of David Sudary, Ginsburg, and Ralis, using the residues of Eisenstein series. Okay, so that's how the Eisenstein series enters the picture. And now you can ask, what is the relation between realizing this representation as a residue of Eisenstein series of a bigger group H, and the model which arises from local, which is a tensor product of functions on omega, restricted tensor product with respect to those spherical functions. So you want to relate those, or rather define the automorphic realization of this space via certain theta series. This is highly related to the Eisenstein series. I don't have time to talk about it, but this was also the topic of an investigation of my project with David Kazhdan. And in principle, those Fourier coefficient, using this Fourier transform, one should see the variation of Poisson summation formula for the four functions on a cone. So let me stop here. Thank you very much.